Hi everyone, and welcome to part 3 of today's lecture, lecture 9. We're going to look a little bit about the geometry of a linear transformation, and we're going to look specifically in the case of R2. Now, many geometric transformations that you could perform, like reflection about an x-axis or a y-axis, or dilation, which means stretching things out, a rotation, which is rotating about the origin, or a shear is where you kind of knock things over, in R2 are actually examples of linear transformations. And so I thought I would work out one example in detail. In particular, I would work out the example of a rotation in R2. So here's the example that we would like to look at. So we're going to fix some angle phi. And what we're going to do is we're going to look at the transformation from R2 to R2. So we're going from the plane to itself that takes each point and rotates each point in R2 about the origin through the angle phi. So there's two things that we want to do. First, we want to show that T is a linear transformation. And secondly, we want to find the standard matrix of T. This would tie into the first part of our lecture where we showed that every linear transformation can be written as a standard matrix. So get us going here, let me just kind of draw a picture of what's happening here. So we have, say, some sort of vector, x, y, inside of R2, and we fixed an angle, phi, and what we're doing is we're rotating this point right here over to this point right over here. So this is x prime, y prime. And so what we want to know, or sorry, let me rephrase that. So we're given a vector xy and it's sent to some vector x prime, y prime. And what we want to be able to do is express x and y, or the new x prime and y prime, in terms of the original x and the original y. Okay, so let me write this down, is we need to express x prime and y prime in terms of the given information, which is x, y, and the angle of rotation is phi. So at first glance, it may not be clear about how one might go about doing this, but the trick that we need here is we need to notice that there's another way of representing this particular vector right here. So I've introduced a new angle, theta, which is telling us how much the original vector would rotated off of the x-axis. And the other piece of information we're going to capture is the length of this vector. So we're going to let r be equal to x squared plus y squared, and that's going to be the length of the vector xy. Okay, and that's just Pythagorean's theorem coming in here. Now, there should be also clear, without too much difficulty, to see that this is actually the same length of the second vector, because all we're doing is we're rotating this line in this direction. So we're not stretching this line at all. We're keeping the length the same. So both this line, first red line and the second red line, both have the length r. And now using some trig, all right, we can actually express x and y in terms of this length and this vector theta. All right, so let me write that out. So we have that x is equal to r cos theta, and y is equal to r sine theta. Okay, so that gives us a different way of expressing the x and the y. And now how do we express the x prime and the y prime? Well, we can do the same sort of thing. X prime is r, and then what is the angle? Well, it's going to be cos theta plus phi, okay? It's the sum of these two angles. And y prime is equal to r sine theta plus phi. Okay, so we're heading off in the right direction. We now have x prime and y prime. We somehow see the theta showing up, but we don't see the original x and y showing up in our expression. Now, to get around this, what we need to do is we need to somehow use a trig identity to replace these two expressions, cos theta of phi and sine theta of phi. And that's, I've actually done the work over here, is that, here, let I'll underline it here. This part here and this part here, I can use a trig substitution to replace them. And so this is the corresponding replacement. So x prime is equal to r times this expression. And if you expand it out, right, we get that you get r cos theta, right? Oops, let me go back here. I get r cos theta, r cos phi minus r sine theta, r sine phi. And if you look at this carefully, what is r cos theta? Well, r cos theta is x, and y is r sine theta, so we see that inside of here. So this is actually equal to x r cos theta. And minus y. Sorry, actually the r is gone. There's no r right here. Get rid of those guys. Should have x, and then I have this guy expression here is y, and so I have y sine theta. So the r kind of gets absorbed into the x. And similarly over here, when I do all the simplification, I'm going to end up with y cos theta plus x sine, sorry, not theta, phi. I end up with y cos phi plus x sine y. So putting all the pieces together, the vector x, y will get sent to x cos phi minus y sine phi, and the y coordinate will be y cos phi minus x sine phi. Okay, so there you go. There's my expression, except this should have been a plus. Make it right there. So that's my how to rewrite this linear transformation on the other, or this transformation on the other side, about taking a vector x and y and figuring out what x prime and y prime are in terms of the original x and y and the angle which you rotate it. Now I'm going to actually leave some details for you to check. Is you can check this is a linear transformation. Okay, and one thing you really want to see is because the phi is fixed, this is a number, this is a number, this is a number, and this is a number. Those actually aren't changing at all. So now if you assume that this is a linear transformation, we can actually figure out what the standard matrix is. So for a standard matrix, you first have to plug in each of the the standard basis elements. So when I plug 1, 0 into this expression, I'm going to get cos phi, and downstairs I will get sine phi. And when I plug in 0, 1, I will get minus sine phi and cos phi. So those are actually going to be the columns of my matrix. So I get cos phi, sine phi, and here I'll have minus sine phi and cos phi. So just to kind of summarize here is what's happening here is we are now taking any vector x and y, we're multiplying it by this matrix right here. And this is a matrix of numbers because the phi is fixed, so we can compute all of these values. And I multiply the x and y by this matrix, I will get a new vector, and that will be the coordinates of the vector that I get after I rotate x, y by angle phi in the plane. So this gives you just kind of one example of a linear transformation and its connection to geometry in the plane. You should take a look in the textbook. There's a whole bunch there's 2-3 pages looking at various geometric transformations like reflections, dilation, and so on. And they give you the matrix that you should use in order to perform one of these geometric transformations. So let me just write that in your notes here. So see the text for other matrices. Okay, so that would be kind of a handy thing just to know. Okay, in the last part, we're going to look at one-to-one and onto-ness.